Polynomial functions are some of the most important functions in mathematics. They can actually be used as building blocks for all other functions using what's called a Taylor series. That's a pretty advanced topic, so we're not going to be looking at those. So in addition to these functions being building blocks, they're also some of the nicest functions to work with because of how they behave. All polynomials are in this form. Yeah, of course, capital P for polynomial, and then we have some statement here. Now, these coefficients, as they're called, of course, an minus 1, an minus 2, all the way on down to a2, a1, a0. These coefficients are just going to be real numbers. They're not going to be complex numbers. If they were, we could not graph them, and we want to graph them. Now, the powers, you can see is 0, 1, 2, all the way on up to n minus 1, or n minus 2, n minus 1, and then n. These are all going to be whole numbers, or numbers in the set 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You'll never see negative numbers for polynomials, and you'll never see decimal numbers. So negative numbers actually give you what are called rational functions. So like for instance, x to the negative 1 equals 1 over x. This is not a polynomial. If you see that in an expression, it cannot be a polynomial. And the same thing is true for anything like 1.5, for instance. This is the same thing as x to the 3 halves, which is the same thing as the square root of x cubed. And square roots are not also going to be in polynomial functions. So you have to have just 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, all those things on up. That is what gives you a polynomial function. Now, looking at this form here, and we're going to look at two special cases. If the highest value, so the idea here is that we have some highest value on the power. Every polynomial will have some highest value. And then that is what we're looking at. So the highest value could be 1. In that case, all this stuff is just dropped. And you just have this statement here, which is what I have here in this case. And then what I can do, x to the 0 is just equal to 1. So that means that this just becomes this. And I'm going to rename a1 to m and a0 to b. And that's what gives us Lx equals mx plus b. So linear functions are actually the simplest type of polynomial. Likewise, if instead the highest power is this one, so we're going to have this statement, and you're going to, of course, ignore all this stuff because it's not there. The highest power is going to look like this. And we can rename, once again, this just goes away to 1, or sorry, 1, so it multiplies by that. And I'm going to name this just A, B, and C, and that gives us the quadratic function. So linear functions, quadratic functions, really you can look at cubic and then quartic functions and so on and so forth, but anything really higher than quadratic is really just thought of as a general polynomial function. And so that's what we're going to be looking at. Now, the basic form of a polynomial is just called the monomial function. And this is where you have only the highest term. So the previous ones I showed you was linear and quadratic. These are not monomials unless this was gone and these two were gone. Then they would be monomials. But the monomial function is a very simple polynomial where the highest power is the only thing there. So we're going to have m of x equals an x to the n, and that's it. There's no other terms in this polynomial function. And really, this is one of the key things to keep in mind here with a polynomial, is that much of its behavior is dictated by this highest term. So when you're looking at a polynomial function in general, much of the behavior that you're looking at is going to be dictated by the highest term, the highest power on x. We also know, of course, that this is a degree n polynomial. This one, the linear function, was a degree 1, and a quadratic was degree 2. So the highest, the degree, that term really dictates a lot of the behavior of the polynomial. that means that the leading coefficient, an, also dictates a lot of the behavior of the function because it directly impacts it. And that's what monomial functions are. You can see we have 4 of them here. We have x squared, x cubed, negative x squared, and negative x cubed. And for x squared, you can see we have a domain of everything. And we have n behaviors that goes up to the left and up to the right. So we can say, of course, as n goes to negative infinity, as x goes to negative infinity, m1 of x goes to positive infinity. And the same thing is true as x goes to positive infinity. It also goes, m1 also goes to positive infinity. So that's the n behavior for x squared. X cubed, the domain is everything, because you can cube any number. There's no issues there. And the n behavior is down to the left and up to the right. So we could say x goes to negative infinity, m2 of x goes to negative infinity, and of course, as it goes to the right, the function goes up to positive infinity. Down and up. Okay, now negative x squared, negative x cubed, we know from function transformation that really all this is doing is it's flipping the function vertically, which means well, that the domain's not changing from this because you can still square any number and then give it a negative sign. But now the end behavior flips. It goes down and down. So we have, as x goes to negative infinity, and as x goes to positive infinity, m3 of x goes to negative infinity. So the end behavior is the same for both sides. And then, of course, the last one is as x goes to, the domain, of course, is at negative infinity to infinity. As x goes to negative infinity, m4 of x goes to positive infinity, right? It goes up to the left. And as we go to the right, as x goes to positive infinity, the function goes down. So it goes to negative infinity. And I'm showing you these 4 graphs because these are kind of the archetypes of the polynomial functions. So a lot of the even monomial functions or even polynomial functions have similar behavior as x squared or negative x squared, depending on, of course, if the leading coefficient is positive or negative. And the odd polynomials will follow x cubed and negative x cubed. So keep these parent functions in mind and the flipped versions of them, because that's going to give you a lot of intuition into looking at how polynomial functions in general work. Okay, so what are the end behaviors of these functions? Well, as I said, all even monomial functions follow x squared and negative x squared, and then all odd follow x cubed and negative x cubed. This is a monomial function. It's just some an x to the n. This is, of course, it has degree 1003, but that's just odd degree. So we know n is odd. And we also know the leading coefficient here is negative. So an is less than 0, which means it's going to follow, it follows negative x cubed for its end behavior. What does negative x cubed do? Well, that was right here. It's going to go up to the left, down to the right. We know, of course, the domain is everything in this function. If we go up to the left, down to the right, that means f1 of x, just do it like this, as x goes to negative infinity, as it goes to the left, the function goes up. As it goes to the left, the function goes upward. And as the function goes to the right, the function goes downward. Or as x goes to the right, the function goes downward, I should say. That's the end behavior. So we know that you can go ahead and graph this on your own. You're going to see that it's going to go up to the left and down to the right. So up to the left and down to the right. That's what you're going to see on the graph. The graph is also going to look something similar to this function here. It's probably going to be stretched from this one. It's already been flipped from the regular x cubed and then stretched in some way. Pretty far actually, since 874 is a large negative number, and then 1003 is going to make it look pretty boxy. But graph it yourself and show that it's actually the case. Okay, here we have an, which I should say really this is A28, just like the previous one was A1003. N just refers to the leading coefficient, and so an is the leading coefficient term. So yeah, A28 is greater than 0 because it's just 1 here, and n equals 28. So this is going to follow x squared. It's even and it has a positive coefficient, so it's going to follow the same behavior as this one here. It's going to go up to the right, or sorry, up to the left and up to the right. So we can do that by saying as x goes to negative infinity and positive infinity, f2 of x goes to positive infinity. Goes up to the left and up to the right. Okay, for the last one, we have, this is just a very large positive number. This, of course, is A7 is greater than 0, n equals 7. This is a number that has 86 zeros after 56, so it's a very, very large number. It's going to follow x cubed, the positive x cubed version. Same behavior as that. Let's go ahead and see that real quick. So it's going to go down to the left and up to the right. So going down to the left is x goes to negative infinity. The function f3 of x, it goes down to the left, so it goes to negative infinity. And then as it goes to the right, the function goes down to the left, up to the right. Now, these functions, because they're simple enough, where you just have that single term, you can actually see transformations on them. Now, I should say that the monomial function transformation, of course, it looks like this. If you're looking at a monomial transformation of a linear function, of course, this is a monomial transformation. N is just equal to 1 here. But this is just a linear function, and so you can just distribute the 3, right? And then add like terms, and you get just 6x plus 2. And 6x plus 2 is way easier to look at, to analyze on its own, rather than looking at the transformation of some linear function. Of course, the linear parent function is just y equal to x. That's just this. So this is a transformation on this, but this is pretty easy to analyze by itself. And so looking at a transformation of a linear function is kind of pointless, in my opinion. And then for a quadratic, this is the vertex form of a quadratic. And this, because b equals 1 here, that's the important thing to note. And how you find the vertex form, b will always equal 1. The vertex form is actually easier to use than looking at a transformation. So I recommend looking at the vertex form and, like for a linear function, just the linear function by itself rather than transformations. Now, if you don't have a monomial function, then sometimes you can rewrite it in this form. As I've shown in a vertex form, you can rewrite a quadratic always into this form. But not every polynomial can be rewritten in this form. So many polynomial functions are not transformations of basic things. Every monomial function is a transformation of the basic monomial function, but most polynomial functions are not. So that's an important thing to keep in mind, that many of the polynomial functions you'll see are not transformations. They're actually different kinds of functions. And I'll show you that. I'll show you why that's the case. But first off, let's look at these transformations. Look at the end behavior, domain, range, and then of course graph them. So this function here, the monomial function, the basic one, is x cubed, because we can see that it has 3 here. And we know that the function transformation, of course, is just a f bx minus c plus d. So a is 1/2. That means it's going to be vertically flattened or vertically compressed by a factor of 2. It's half as big as it is tall. And c equals 3 here, right? X minus c, x minus c. C is 3. That means it's going to be shifted right 3 units. So vertical compress by 1/2. So it's half as tall. And then shift right 3 units. Now the end behavior, that purely depends upon the power. So in this case, n is 3. A is still positive, so we know this is going to follow the positive x cubed end behavior. So positive x cubed, you just go back up to the thing. You can graph it, of course, or you can just look at this table here. This is positive x cubed. It goes down to the left, up to the right. It's going to have the same behavior as that. So down to the left, up to the right. As x goes to the left, the function g1 of x goes to negative infinity. As it goes to the right, the function goes to positive infinity. Okay, domain and range. These are pretty simple to show. It follows x cubed's behavior. I didn't show the range up here, but the range is pretty easy to see. The range for this one is from 0 to infinity, as we've discussed before. This one becomes flipped, so the range for this one is negative infinity to 0. And the range for these is always negative infinity to infinity for both of them. So it follows the same behavior as this one. The domain is going to be everything. The range is everything as well. And you can see that because there's no issue plugging in numbers into here. And if it follows the same behavior, it's going to go down to negative infinity. So all those values are going to be included. And it's going to go up to infinity. So all those values are included as well. So the domain is everything, as is the range. Okay, for g2 of x, we'll graph these things at the very end here. But for g2 of x, we have x to the 4th, so it's going to follow, it's also negative, so it's going to follow the negative x squared behavior. All right, now let's look at the transformations. A is -2, and B, sorry, not B, B is 1, C is 0, and D is -5. So we know this is going to be a vertical flip. And stretch by a factor of 2. And then it's going to be a shift downward by 2 units. Okay, it follows negative x squared behavior. So imagine x squared. X squared looks like this. Negative x squared then is flipped. So this becomes flipped like that. So this is kind of what the graph looks like. It doesn't look exactly like that, but you get the idea. It follows the same behavior. So the end behavior is going to be as x goes to negative infinity, g2 of x goes to negative infinity, and as it goes to the right, it also does the same thing. Now, the domain, of course, is everything. There's no issues with taking a number and, taking it to the fourth power, multiplied by -2, then subtracting 5. The range, however, is a little bit different. We've not talked about how to find the range of these things, but this does look pretty similar to a parabola. It's not exactly a parabola. It's actually a little bit flatter on the close to the vertex, the maximum in this case. It's a little bit flatter. It's not completely flat, but it's a little bit flatter. And you can think of this middle point here as kind of like a vertex. It does have the same idea as a vertex for a quadratic. So we know that it's been shifted down by 5 units. So if it's been shifted down by 5 units, that means that it would originally be located right there on the origin, but now it's been shifted down 5 units. So that means that that point is actually a maximum. And I'll show you this in the graph, but it's a maximum point because just like for a quadratic, it's been shifted down 5 units. The maximum would be at -5. So the same thing is true here. It goes from negative infinity to -5. And once again, I'll show you that so you don't have to just, trust what I'm saying. Okay, this next one we have n is 12, so we know this is going to follow. A is also positive, so it's going to follow positive x squared now. And what are the transformations? The transformations are a equals 1/5, b equals 12, c equals 7, and d equals -4. So there's a lot of transformations on this one. So we know it's going to have a horizontal b is 12. So if it's greater than 1, it's going to actually be a compress. It's going to be a compression by a factor of 12. It's going to have a vertical compression as well by a factor of 1/5. Then it's going to be shifted 7 units to the right and 4 units downward. Now, with all that being said, the end behavior of this function still follows positive x squared. Positive x squared looks like this. So we know that as x goes to negative infinity, the function goes to positive infinity. It goes up to the left and it goes up to the right. Right is towards positive infinity. g3 of x goes to positive infinity. Okay, domain and range. Domain's everything. And the range, once again, this is going to have the similar behavior as the quadratic, the parabola. But this parabola has been stretched and compressed, compressed both ways. That doesn't change the range, however. What changes the range is the shifting. It's shifted 7 units to the right and then 4 units down, which means that this minimum point is shifted down by 4 units. Instead of at 0, it's now lowest at -4. Once again, I will show you that. So let's go ahead and look at the graphs of these guys. There's no reason to graph this by hand. We can just graph them on the software. So this is the first one. Let me actually plot the parent function here. There we go. So the parent function's in red, and the blue is the transformed function. So we've taken this thing and we've squashed it. We've kind of flattened it out a little bit and then shifted it to the right 3 units. So you can see it's flattened a little bit and it's been shifted to the right 3 units, which is what we said here. And the behavior is down to the left, negative infinity to negative infinity, and then positive infinity to positive infinity, up to the right, down to the left, and up to the right. So that is correct. Okay, for the next one, g2 of x is negative x to the 4th. Okay, here are both of these guys. So the red, once again, is just x to the 4th power. And this is our transformed function. You can see up here we had a vertical flip and stretch by a factor of 2, and then a shift downward of 2 units. Sorry, a shift downward of 5 units. D was negative 5. That's the confusion there. Shift downward of 5 units. So it gets flipped. And then, as it said here, it says a vertical stretch by a factor of 2. So if it gets stretched by a factor of 2, that means that these points here are going to get pulled upward. And so it's not going to be as flat here. And then that's actually the case, that this is not as flat as this one. And then it's been, of course, flipped and then pulled down, and then it's been shifted down by 5 units. So that's what our resulting function is. The range for this, of course, is negative 5 is the top, and it goes downward indefinitely. So that's what I have here. In behavior is down and down. So down to the left, down to the right, which is, you can see right here. Down to the left and down to the right. Okay. Okay, and this is our last function here. Let me get rid of that. You can see it's been changed a lot. We have a horizontal compression, a vertical compression, so it's been compressed both ways. It's been shifted right 7 units and down 4 units. So yeah, I just realized that the shifting to the right is incorrect. This is one of the issues with not graphing the function on itself. That's because B and C, if they're both not, if B is not 1 and C is not 0, then they actually interact together. And so what you would do is you take C divided by B, and that's the shift. It's very confusing, I agree. I don't recommend you ever graph these things by hand. So just keep that in mind. This should actually be 7 over 12, because it's C, which is 7, divided by B, so 7 over 12. Let's double check that real quick in the graph. Let's see, 7 over 12. Desmos gives us the exact center of the vertex, 0.5833. Let's just plug it in here. 7 over 12 is 0.583333. Yeah, so that's where it comes from. Very easy thing to mistake when you're not given simpler transformations. The key thing to note here is that you need to graph the function. Don't graph it by hand, graph it using software. Much more accurate, then you can catch errors like this. So it's still been shifted down 4 units. That doesn't happen on the outside. It's only on the inside that it does, which you can see here. It's been shifted downwards 4 units. So it has still been flattened and, compressed vertically and compressed horizontally. It's hard to tell which one's which since there's both compression, but they're both in there. You can see it's a much smaller, peak. This is a lot wider. So and then it's been shifted over and down. You can still see that the range is still -4 to infinity. That hasn't changed even though I made that mistake. And the in behavior is still the same. It still follows the positive x squared up to the right and up to the left. Still the case. Okay, give it a try in number 1.